Hey y'all, let's take a look at curvilinear motion. So we're on a non-linear path, just your generic path right here. Just put the origin at the starting point for right now. But imagine some particle traveling along. It's on a little bit of a curve right there, some mass, and it travels some distance s. Okay. Well, we're going to look at the origin as being at the particle in these problems. So it's a little different. We're not going to put the origin somewhere in space over here and call this 0, 0. We're just going to call the center of the particle our origin and assume we're talking about some general planar motion, so some curved path or something. In this case, I mentioned in a previous video, we have to not only consider the fact that something accelerating on a path can have a linear acceleration. Maybe if it's on a straight path and you're flooring it in your car or slamming on the brakes, that's just what we're going to start calling a tangential direction. And we have what's called a normal direction. So this is the unit normal direction on this particular point on the curve, and let's say it's also speeding up while going around the curve. Then we have a normal and tangential component, and I'll derive those in just a moment. I also want to take a look at something. I'm going to introduce rho in a bit. And let's go ahead and look at it now. Rho is going to replace radius for all the problems you may have done in high school. This path is some function of x and y, or some other coordinates, and it has some radius of curvature rho 1 right here. It may have some different radius of curvature rho 2 right there. It looks like the radius of curvature is a lot tighter right here. So rho 2 or rho 3. And right there, maybe some radius of curvature 4, and so on. And then on this side, the radius of curvature would be like this. I'll show you how to calculate those if we know the path function. Main thing, we have two components when we look at acceleration. We need to worry about the component causing the turn in the unit normal direction, and if we're speeding up along the path at the same time, we need to worry about the tangential direction, which would be in line with the velocity. Okay, if some particle is moving along this path and s is a function of time, then we said earlier the velocity is always tangent to the path. If I'm going to go ahead and try to redraw this same path, kinda. If it has some velocity tangent to the path and moves from one point to another, let's say this is some rho to some other, let's call it the same rho for this instance, that's going to have caused some acceleration. It definitely accelerated because the vector changed. If the vector changes either direction or magnitude or both, that means we had an acceleration. So that velocity, we will say, is equal to just the velocity, the magnitude, and we're going to put it in the unit tangential direction. So that's we're multiplying the magnitude by a vector that's one long in the tangential direction. This one right here, the same as the drawing from earlier. And don't forget, we can call the velocity s dot, right? The time derivative of position. Alright, when we look at acceleration, we will have a component like this, in the normal direction and a component in the tangential direction. So something caused it to curve, and let's say we're speeding up on the path at the same time. If you remember, acceleration is equal to v dot, and we have we have to consider two components now. Just like if we had an x or I and j component, not an x and y component, we now have a tangential component in the unit tangent direction plus a normal component in the unit normal direction. Alright, here's the trick. So this is a magnitude or a number right there, just multiplied by the direction, a number multiplied by the direction. The acceleration in the tangential direction is literally how fast you're speeding up. It has nothing to do with the curve. At that instant, you're not curving. You're just talking about how fast you're going in the vector that lies in the same direction as your instantaneous velocity vector. And we can say that that is then just equal to v dot, or the acceleration, or just the regular acceleration that we've been working with our whole lives. And if we wanted to, we can use the fact that the acceleration in the tangential direction times ds is equal to v dv. So we had a constant acceleration or a acceleration as a function of time, we can use this equation right here. Then we need to figure out, what do we put in for the normal component? The normal component is the velocity that it's traveling as it goes around at that instant on the corner. This has to involve a turn, divided by rho, the radius of curvature, which is what I drew out earlier, so I didn't have to draw it again. We need both of these. We need to know how to calculate them, we need to know what they mean, and be able to put it back into this vector form. And if you had some particle on a path, we'll say the particle's right here, it's starting to curve a little bit, so maybe it has some acceleration in the normal direction, it's speeding up, so it's got some acceleration in the tangential direction. By adding those vectors together, tip to tail, I get my acceleration. That acceleration is equal to the square root of the components squared and added up. So just like if we had I and j components. The next thing we need to discuss that's really important in this section is if the particle is moving in a straight line only, and let's say it's accelerating, that means the normal component of acceleration is equal to 0, and that's because the velocity is equal to 0 and the normal component is equal to v squared over rho. So we just don't have one. Now, we don't have to be accelerating also to have a normal component. The normal component is the constant velocity squared over rho. So make note of that too. We could be cruising around the corner of a turn at some, pretend this is some constant radius, and as long as we don't change our speed, we're still accelerating. So make sure you understand that. We have some normal component at all times pointed towards the center, causing us to turn. And that's usually caused by, or always caused by a force, and usually caused by like a force of friction in this case or something. A tension on a string can change its path. We'll study forces next chapter, plenty. So let's look right here. In this case, on the turn, we had a normal component and a tangential component because it's speeding up. But let's say the path straightens out. When the particle's over here at some maybe p prime, then it only has a tangential direction of acceleration. There is no normal direction. Even though it has a v, there's no v squared over rho. Okay, now the last thing I want to show you is how do we calculate rho if we have a path function. And we do that with this formula. If we have y as a function of x, so we've seen the balloon had, I think, x squared over 10 as our path. Then we had an elliptical path. Well, we can take the derivatives of those and find the radius of curvature. So the formula would be 1 plus the first derivative, dy dx squared, all raised to the 3/2 power, divided by the second derivative. I'll do an example next. You do not have to memorize this formula. If we were in physical class right now, I would definitely give you that formula. Know how to use it though. Take the derivatives of the path, put them in, evaluate at the point, so I guess that's to be noted. Evaluate, that's not how you spell evaluate. Evaluate at some x value, because each of these is a function of x, so taking the derivative will either give you a function of x or maybe, and very often, a constant on the bottom. If you're working with the parabola x squared, first derivative will give you 2x, and the next derivative will give you 2, so you end up with just a number on the bottom, nothing to substitute. If you have a function of x at the top still, then we would evaluate it at some x value. Alright, thank you.